Hey guys, welcome to video 2 of the fluid mechanics series. This is the second of 4 videos on hydrostatic fluid mechanics, that is fluids that are not moving. If you haven't yet watched the first video, please go back and watch that because it gives some very important foundational materials and definitions that we will build on in this video and the next two. This video will specifically deal with hydrostatic pressure, and that is something we very basically described in the last video, which was more focused on just pressure and the definition of it in general. Now we're going to take a look at it when we have a static fluid. How is it that we can understand the pressure in that fluid? It turns out that understanding hydrostatic pressure is very important for hydraulics, which is a very useful application of this principle. So let's start. So we ended the last video talking about the definition of pressure, which was the amount of force exerted per unit of area. Just like we discussed in the last video, where instead of writing the mass of a fluid, we're now going to rather focus on writing the mass as the density times the volume of the fluid. Similarly, instead of writing just force like we're used to doing in physics, we're actually going to write that as pressure times area. You obtain that expression, pressure times area, by manipulating the original equation like this. Let's go back to forces for a minute and balancing forces. If I have a box with an applied force pushing it to the right and an applied force pushing it to the left, let's label those force A and force B. As you can see how I've drawn it, if force A is greater than force B, then there will be a net force in the same direction as force A. And the value of that net force will be force A minus force B. If there's a net force, then the object, in this case the box, will accelerate to the right. If, however, force A and force B are equal, then the box will remain at rest. Let's take a look at this from the perspective of pressure in a fluid now, using the same fundamental ideas we just discussed. Let's begin by making some observations about the fluid in this round bottom flask. For example, let's make this fluid water. One thing I notice about it is that it's not moving. In other words, all the particles of the fluid as a whole are stationary. In our next major unit on thermodynamics, we'll take a closer look at the fact that the particles in the fluid are actually vibrating place and moving around each other, but as a whole, we can say that the fluid is static. So let's isolate a little amount of water in this flask. We'll draw a square, and we'll say that we are going to focus on just that little piece of water to understand the hydrostatic pressure. If the hydrostatic pressure was not at equilibrium, the water should be moving. However, it's not moving. So let's draw the same example that we did before, but now in terms of pressure. If I take this tiny little block of water and I say that if I apply a force to the right side of the block of water, and instead of force now I'm going to write pressure times area, that expression we used before. And if I think of the water pushing back on the other side, I'm going to write that as pressure times area as well. Now that little cube of water has an equal area on both sides. So if I was to say that the pressure times the area, also known as the force, is the same on both sides of that block of water, then I could cancel out that area and I would show that the pressures are the same on either side of that little block of water. So at any point within the fluid, the pressure is going to actually be exactly the same. Now this only works if the fluid is enclosed, and it only works if the fluid is static. When the fluid starts to move, or there are other influences that we take into effect, then we will have to recreate a model that is different than this one. This model is oftentimes called Pascal's Law or Pascal's Principle. Stated more formally, Pascal's Principle says that in an enclosed hydrostatic fluid, the pressure is transmitted everywhere in the fluid undiminished. Changes in pressure will be felt the same everywhere throughout the fluid. This phenomenon, this law, allows us to apply it to lifting objects and making it easier to move really heavy things through hydraulic systems. Let's take a quick look at that. The picture that you see here is known as a hydraulic lift. Basically, it's one enclosed container that has an opening on the left side that is very large and an opening on the right that is very small. One way that we could describe the differences in the opening is we could say that the area of the large side, the cross-sectional area, is quite large, and on the right-hand side, the cross-sectional area is quite small. Now we just established that in an enclosed fluid that is static, a change in pressure at one place in the fluid will be transmitted undiminished. In other words, it will be the exact same change in pressure as any other place in the fluid. This means that if I change the pressure at position 1, I change the pressure at position 2 by exactly the same amount. Let's now substitute in our expression for pressure. Force divided by area. According to our picture, if area 1 is much greater than area 2, that means that force 1 will have to be greater than force 2. Otherwise, this will no longer be an equality. A way you can think about this is like simplifying fractions. Saying 100 divided by 10 is the same thing as saying 10 divided by 1. So if we look at each ratio independently, what we're saying, if we apply it to pressure, that when the area is 10, I can exert a force of 100. But when the area is just 1, I can exert a force of 10. If you're thinking simple machines, you're thinking right. Simple machines make input forces much less. In other words, we have to exert less effort to achieve the same result. So, according to the hydraulic press, I can push with a low amount of force on the smaller side and raise something that's very heavy or a large amount of weight force on the bigger side. Basically, what the enclosed static fluid is doing is multiplying my force throughout the fluid. Sounds too good to be true, doesn't it? How can I multiply my force? In other words, how can I push with, say, just my hand on the small side and lift a car on the large side? It turns out that what I made up in force, I lose in distance. So what this means is that if I want to raise the car just a tiny amount, I actually end up having to push much further down on the smaller side. Now that works out better for me because I have to exert less force at every instant. Let's very quickly look at how that works. It's basically conservation of matter. If I push down on the small side, I displace a certain amount of volume. Well, if this is an enclosed, incompressible fluid, the exact same amount of volume has to displace everywhere in that fluid. In other words, the spaces that the molecules are taking up when they get pushed have to move somewhere. So mathematically, I can write it this way. The change in the volume on, let's say, side 1 has to be the same as the change in the volume on side 2. I'm going to substitute in, instead of volume, area times height on each side. So we'll make this area 1 times height 1 equals area 2 times height 2. A1 and A2 correspond to the cross-sectional areas of each end of the pipe, and H1 and H2 correspond to the height or the depth that I press down into that side of the fluid. So according to my diagram, if A2 is much bigger than A1, H2 will have to be much smaller than H1 to maintain an equality. In layman's terms, I have to push very far on a small area to raise something only a tiny bit over a very large area. However, doing so will allow me to push with much less force. This is all true because of Pascal's principle. In the next video, we'll explore how depth within a fluid affects the hydrostatic pressure.